So we've demonstrated that as samples get larger, they tend to become more reliable. But that raises a question of how big of a sample should we draw? What makes sense in terms of an optimal sample size? So let's just again kind of refresh, right? Bigger samples deviate less from the true population value. That as our sample size gets larger, the standard error, right, the amount of average miss on the sampling distribution, which is how samples behave, gets smaller. So samples kind of compress in around the true population value and become more reliable. And intuitively, that makes sense because if you flip 10 coins, the odds of getting 8 heads or 80% heads is not crazy, maybe not super likely, but not crazy. If you flip 1,000 coins to get 80% heads would be a pretty unusual thing to have happen. That would suggest that coin is behaving in odd ways, right? So just intuitively, we sort of get a sense that as the numbers we're working with in both random processes are larger, it's harder to get really bizarre things happening. But that doesn't mean that a bigger sample is always a better sample. What statisticians have found is that after 30, a sample will behave according to the sort of logic of sampling, of a bell-shaped standard deviation or a bell-shaped distribution in terms of the sampling distribution. They can calculate reliably the standard error. So if you're thinking about a random sample, you want at least 30. At about 100, people start noticing that there's some reliability with that sampling. And at about 1,000, that tends to be where people sort of notice a diminishing returns effect coming into play, where if you get a sample going from 100 to 1,000, you see some real gains in terms of precision in those samples, going from 1,000 to 1,900, so increasing by another 900 cases, or even to 2,000. You get gains in efficiencies and precision, but it's not quite as dramatic. And that has to do with that sort of equation where we're taking the square root of the size of our sample. And so there's a diminishing returns effect. And so to get the kind of gains that you would get from going from 100 to 1,000, maybe you have to go to 10,000. And at that point, the cost of each additional sample of those larger samples starts becoming prohibitive. And so people tend to sort of focus in on samples that are around 1,000. And that kind of makes sense. I could maybe talk about it a different way to maybe help visualize it, although I'm not entirely sure that this is a helpful graph. I found this in a statistics textbook a while back, and it kind of clicked for me what was happening. This is sort of a charting of what happens when somebody draws a sample. And so the true population value of this data set that they're drawing from on this particular property, the true population value is 64.5. That's that sort of dotted red line. And the first case that they draw is a little bit below that. It's like 64.2 something or other. And then they draw another case, and that kind of brings them a little close to the red line. By about case 4, they're a little bit above that dotted red line. They've drawn 4 cases, and the average is a little bit high. But then they get a string of sort of particularly low cases. And that average from that sample starts dropping and dropping and dropping. And then it kind of rebounds. And by about 50, you're pretty close into the true population value. But here's what I took away from that, that graph. The changes that we get, the bouncing around that we see, it starts out really volatile. Each new case is adding a lot of new information. And so we're getting big changes. And so if we draw a really wonky case, it has a big effect on the overall sample. But after about 50, or maybe even after about 100, drawing additional cases isn't really changing the results in meaningful ways. Yeah, sure, there's some edging it up and down and shifting it a little bit, but those changes are really pretty small. And after about 1,000, the effect of drawing an additional case isn't altering our results in any noticeable way. And so after about 10,000, you can't even tell. So what this kind of visualized for me is that as sample sizes get larger, the benefit of potentially drawing more cases, adding more information into our sample, it starts to be negligible. Yes, we could maybe get more accurate information with a larger sample, but you got to get a lot larger sample to sort of make up for any little oddities in your current sample once you've sort of reached that 1,000 point. I can maybe illustrate this a third way. I do a lot of weighting of public opinion surveys to try to make the initial results match sort of what we know about demographics. And as part of that, I have to calculate for people what their standard errors are and what their confidence intervals are. And so I made this handy little Excel spreadsheet to help myself with this. And this is calculating standard errors for a proportion. And so the equation we've looked at in the past was for an average. For the proportion, it's a little bit different. It's the square root of the proportion, then 1 minus the proportion, and then we divide that by our sample size. So it's a little bit of a different formula. I've added in this design effect piece, which if we're not weighting anything, we can just make 1. And that adjusts things, but we don't necessarily have to talk about that right now. What I wanted to flag right now is that when we're thinking about our sample size, you can pay attention to this line right here, and maybe even this piece right here. One thing that happens with standard deviations of proportions is that as the proportions sort of move away from 0.5 or half, our results get a little more reliable. Not a huge amount, but enough that it's worth paying attention to. But if a 50-50 split is roughly the largest you're going to see for the standard errors. And so we typically use a 95% confidence interval. That's where we go out 2 standard deviations on a sampling distribution and say sort of within this range, we're pretty confident, 95% confident that we've got the true population value. You can go out not quite as far and say I'm 90% confident. You can go out a little bit further and say I'm 95% confident. It really depends on what you're choosing to do, but the standard is sort of to go out 2 standard deviations in the sampling distribution. Now, if you take a sample of 100, your standard, I should say, your standard deviation on the sampling distribution and a confidence interval of 95% is going to give you a margin of error of about 10%, which is probably too high to be able to say anything useful. But if we jump to 500, let's cut that down to about 4.4%, which is starting to hone in on something that looks about useful, that I could look at that and say, well, I can tell if, one category or candidate or position is moving or changing in a major way. I could probably pick that up with that kind of a result. And if I go to 1,000, that result here falls to about 3.1%. And so there's a couple things I think are worth noting, right? So when we went from 100 to 500, when we added 400 cases, we cut the confidence interval by more than half. We cut it by 6%. When we went from 500 to 1,000, added another 500 cases, we were able to drive it down 1 more percent. If we were to go from 1,000 to 2,000, we've been able to drive it down about 0.9%. So getting a pretty accurate result, 0.2 or 2% for our confidence interval is pretty good, but we've had to sample twice as many cases to get to that point. And so a lot of folks who do public opinion sampling tend to use 1,000 or 500. And there's sort of a fun little advantage of that, or something, an intuitive little trick with that. And that is that a lot of the things that we're interested in sampling tend to be proportions, right? Proportion of the population that feels the country's on the right track or the wrong track, proportion of the population that wants to vote for candidate A versus candidate B. And we tend to sample in races and situations where things are fairly close. And so they tend to be in this sort of 50 to 40 range for proportions. And if you're in that 50 to 40 range and you're sampling 1,000, your confidence interval is going to be around 3%. And so if you pay attention to samples, what you'll oftentimes see is the little fine print that says plus or minus 3%. That's our confidence interval. And that number isn't coming out of sort of nowhere. That number is coming out of a decision by the polling firm to use a 95% confidence interval to sample a situation that's fairly close, 40 to 50% in terms of the proportions, and to use a sample size of about 1,000. And we see that over and over and over in public opinion polling. And hopefully now you get a sense of both why that number is what it is, but also why it's not smaller, and what it would mean to try to drive that margin of error down to a more precise level.